Welcome to the GTU. I'm Kevin Bosse with Tudor Gold Corp. We're developing the Goldstorm copper-gold porphyry deposit at our Treaty Creek project. It's been a well-rounded discovery at Treaty Creek over the last 5 years. I'm here to talk about a brand new discovery of the Supercell 1 high-grade gold domain. This talk will contain forward-looking statements, so please refer to our most recent 43-101 technical report from February of 2024 and our news releases for more information. So I'll start by introducing the regional and deposit scale geology to provide a framework for interpretation of the new supercell discovery. Our flagship Treaty Creek property is located in the heart of the Golden Triangle and neighbors Newmont's currently operating Brucejack mine, the past producing SK Creek mine, and Seabridge Gold's KSM Advanced Development Project. Treaty Creek is located on the ancestral territories of the Tsatsouat, Skikamaha, Tahltan, and Nisga'a nations, and we have a strong working relationship with all the local communities. So this area of the Golden Triangle is known as the Sulphurets District after the Sulphurets Thrust Fault, the major structural control of hydrothermal mineralization in the area. In this map, you can see the Treaty Creek project boundary and where our Goldstorm deposit, shown in solid red, as well as our other targets in translucent red, sit in relation to the other major deposits in the district, including the KSM deposits in blue and Brucejack in yellow. The Goldstorm deposit is the fifth giant gold copper porphyry discovered in association with this fault after the KSM deposits. Of note, the Goldstorm deposit is substantially higher grade than the other porphyries in the district. And luckily for us, we're also substantially closer to the highway road access. You can also see the access road that Seabridge is building right to our doorstep as part of their own development strategy. To highlight the magnitude of the Goldstorm discovery, our current indicated resource comprises of 27.9 million ounces of gold equivalent at an average grade of 1.19 grams per ton. And that itself consists of 21.7 million ounces of gold at 0.92 grams per ton, 128.7 million ounces of silver at 5.48 grams per ton, and 2.87 billion pounds of copper at 0.18%. Interestingly, these deposits occur in a perfect periodicity of 2-kilometer intervals along the Sulphurets, with a promising perfect storm exploration target filling the gap between the Iron Cap and the Goldstorm deposits. Looking at the regional geology, on the left is a geologic map showing the location of Treaty Creek, and on the right is a snippet of the geologic timescale showing ages of the BC deposits, as well as timing of our local stratigraphic column. The Goldstorm deposit is hosted in rocks of the Lower Jurassic Hazelton group, specifically intermediate volcanics and volcaniclastics of the Unuk River member. Goldstorm was discovered proximal to the Triassic-Jurassic unconformity, known as the Khyber Red Line, which once again shows its importance as a space-time stamp to locate major deposits in the Golden Triangle. Rhenium-osmium geochronology by MDRU dates Goldstorm at 194 MA, a very similar age to many other porphyry-type deposits in BC. Taking a closer look at the deposit scale, nearly all of our knowledge of the Goldstorm deposit has been attained through drilling, with 190,000 meters drilled to date. Mineralization was discovered in the footwall of a major thrust fault, interpreted as an extension or splay of the Sulphurets thrust. This meant that the deposit was a blind discovery, hidden by the unmineralized hanging wall rocks and by the Treaty Glacier. The blue outline here is the footprint of our 2024 updated mineral resource estimate. Copper grade is displayed on the blue histograms along the drill hole traces, and gold grade is also displayed on the drill hole traces according to the legend in the right corner. You can immediately see 3 distinct mineralized domains in cross-section, including a central copper-rich domain surrounded by an upper and lower gold-rich domain. The central copper-rich domain, highlighted in orange, corresponds to our central CS600 potassic intrusive complex. The upper gold-rich domain, highlighted in red, corresponds to the 300 horizon, and the lower gold-rich domain in yellow corresponds to the DS5. And I'll be looking more at the mineralization of those domains in a few minutes. Early on, we found that the deposit was bounded by 2 significant thrust faults, known as Treaty Thrust Faults 1 and 2, or TTF1 and TTF2. TTF1 dips 45 degrees to the northwest, and TTF2 dips 50 degrees to the north. The host rocks are dominantly intermediate composition fragmental volcanics of the Lower Hazelton volcanic pile. Above TTF1, the rocks are dominantly altered by hematite, chlorite, and carbonate and are barren of mineralization. Below TTF1, pervasive mixed chlorite, sericite, carbonate, and potassic alteration dominates. The high permeability and porosity of this host unit makes it an excellent host for porphyry gold mineralization. Alteration through most of the deposit is very intense and has made recognizing lithology and geological relationships very difficult. Tudor is currently working with the MDRU at UBC to learn more about the geochemical characteristics of the deposit. Alteration mapping is being achieved through use of teraspec shortwave infrared analysis of drill core. This initial interpretation supports a distribution typical of the classic porphyry model, with a core potassic intrusion-related zone and an upper muscovitic sericite dominant zone, all surrounded by a mixed propylitic alteration. Here's a comparison of our current Goldstorm alteration model and where it fits into the classic silico porphyry alteration model. This model did prove its worth as a vectoring tool during the Goldstorm discovery. We continuously drilled the upper sericitic and chlorite dominant assemblages and just nicked this porphyry unit. But we knew something very big was lurking under there, so we kept following the alteration vector, drilling deeper and further, and finally tapped into a dream interval. Drilling this interval was mind-blowing. We knew we finally found the heart of the deposit, and so far, we had just found the tip of the iceberg. We were getting box after box of this textbook quartz chalcopyrite stockwork veining in a potassium-blasted porphyry intrusion. This interval ran right down the pipe and returned 0.91 grams per ton gold, 5.65 grams per ton silver, and 0.53% copper for over 732 meters. Just crazy. Here are a few other examples of the spectacular mineralization we see within the core of CS600. From typical quartz chalcopyrite B veins and bornite magnetite shells to atypical massive hydrothermal breccias with this chalcopyrite sulfosalt stockwork, to late quartz carb veins that host visible gold. So CS600 truly is the heart of the system and comprises of multiple diorite to monzonite intrusive porphyry stocks, intrusive breccias, and hydrothermal quartz carbonate breccias. Mineralization consists of chalcopyrite, pyrite, bornite, and sulfosalts with rare visible gold. A near-surface sericitic argillic alteration transitions to potassic dominant alteration at depth. For reference, here's our updated mineral resource estimate and the 3D block model that it's based on. I already mentioned the numbers, but I'd like to point out the significance of the CS600 domain, which contains 2.7 billion pounds of copper at 0.31% average grade, as well as 10 million ounces of gold at a 0.78 average grade. CS600 could be a mine in itself and has the potential to be a great target for block cave style mining. So looking at the other main domains, this photo is showing characteristic 300 horizon drill core with a dominant gray QSP alteration affecting fragmental volcanics. The highest gold grades are associated with quartz carb veining that frequently bears sphalerite, galena, chalcopyrite, pyrite, and occasional visible gold. A consistent low-grade mineralization also occurs within fine-grained disseminated pyrite. And the DS5, which is a dominantly hydrothermal breccia-dominated domain, also consists of a strong dark QSP alteration with occasional hematite dusting, overprinting a background propylitic alteration. So to sum it up, the Goldstorm deposit is a large copper-gold porphyry with consistent grades within domain boundaries, as well as many higher grade pulses throughout. The deposit is huge and currently measures 2,600 meters in strike, 1,200 meters in width, and 1,500 meters in depth. Just look at the scale bar in the bottom right. And we still haven't found the end, so it remains open. Our resource is comprised of 7, and counting, discrete domains that are categorized by mineralization, metallogenic composition, alteration, and lithology. This image is a down-dip view of our working 3D model, and you can see each of our constrained faults and domains color-coded for reference. CS600 in orange in the center, 300 in red above, DS5 in yellow below, along with Copper Bell in blue and Route 66 in green. And that brings us to the addition of the 4 stacked breccia systems of our newly discovered Supercell 1 domain, which I will discuss for the rest of the talk. Our first encounter with Supercell 1 was early in the 2022 drill campaign. That program was designed with one main objective: to drill off the CS600 potassic core and build a world-class copper-gold resource. Hole 134 was a massive 200-meter step out to the north, and we were initially really disappointed because we appeared to miss that deep pink quartz chalcopyrite stockwork that we were obsessed with. We didn't think too much of this dark gray rock when it first came out, thinking it was another 1 to 2 gram per ton QSP pulse that we often encountered in the 300 and DS5 domains. When we got the assays later in the season, we were floored to find multiple samples grading over 25 grams per ton, and a composite of nearly 10 grams per ton over 25 meters. Sure enough, after laying out the cut core, we found 18 flecks of visible gold associated with quartz calcite breccia veining. Things suddenly got a lot more interesting at Treaty Creek. Naturally, the next campaign was designed to test for more of the high grade. In 2023, we designed a drill plan to continue expanding the CS600 resource while also testing for more of our new high grade find. We were successful. CS600 kept getting bigger, and interestingly, more gold and less copper dominant towards the northeast. And we now had 3 points indicating a high grade planar structure that we coined Supercell 1. Realizing that a high-grade domain would be a game changer to expedite development, we then designed the 2024 drill program to find more, and once again, it worked. 2024 drill results confirm the presence of at least 4 stacked high-grade structures that extend out from the CS600 resource domain. They've been named Supercells 1A through 1D, and here you can take a look at some of the exceptional composites released over the last few months. So, what is Supercell? That's a good question. So some of the key observations we've made about Supercell 1 are, for mineralization, it's a discrete high-grade gold domain that's also enriched in antimony, arsenic, lithium, cadmium, zinc, tin, thallium, and variable copper, silver, and lead. Interestingly, SC1B has a much higher copper and silver presence than the others. And these metals are commonly distributed in very shallow porphyry to epithermal depths. Texturally, it's a unique domain comprised of variable hydrothermal breccia textures ranging from quartz carb vein breccias to massive sulfide breccias to quartz carb crackle breccias through microporphyritic dikes and volcanics. A notable dark gray-black, possibly potassic biotite with or without sericite pyrite overprinting assemblage associated with deeper intervals, and a light beige-green clay-dominant argillic assemblage is observed proximal to most intercepts. MDRU alteration indices correlate the Supercell 1 zone with epithermal advanced argillic alteration packages. Structurally, we know that it contains at least 4 stacked subparallel planes traced across 400 to 800 meters, found at the northern edge of the deposit so far, and they are oriented oblique to the main mineral domains, most notably the central CS600 porphyry intrusive complex. Timing-wise, cross-cutting relationships show that SE1 cuts through CS600 and therefore postdates main porphyry mineralization. The substantially higher gold grade and cross-cutting relationships with the CS600 intrusive are what immediately highlight Supercell as a unique domain within the Goldstorm deposit. You can see this in this image, the solid colored discs of SC1 extending across the domain boundary of the translucent orange CS600. In drill core, this shows as late quartz carb vein breccias cutting through typical CS600 intrusive breccia units. This relationship is the basis of the hypothesis that SC1 is a later stage overprinting mineralization event. Recognizing SC1 in the core shack can be very challenging. Textures range across the supercell intervals. From this unassuming dark gray to black, possibly K-silicate, altered and aphanitic or microporphyritic rock, it kind of ranges. That's what we see here in the right. and you would never guess that that interval had 22.3 grams per ton gold as part of a 9.78 grams per ton gold over 12 meters. This is an example of the vein breccia-style intercepts of SC1. Here, a chaotic quartz carb breccia hosts significant visible gold, seen in the upper right photographs. This interval was part of the discovery interval of 20.61 grams per ton gold and 0.2% copper over 4.5 meters. And this is an example of the semi-massive to massive sulfide veins that can be up to many meters wide. This interval of 6 meters is about 90% pyrite and 10% tennantite, the black mineral that looks to form the matrix of the brecciated pyrite texture. These massive sulfide intervals often show rounding of pyrite grains, which may indicate sign or post-depositional milling by fault movement, and may support the idea that supercell 1 is a later mineral event that exploited an early en echelon fracture set. Again, it is difficult to visually identify alteration assemblages with any confidence in this deposit. It appears that deeper intervals are associated with a dark gray to black potassic type alteration, as well as nearby light beige green clay dominant argillic alteration. Preliminary geochemical analysis supports a strong increase in advanced argillic alteration in the northern margin of the CS600 and in the host rocks surrounding the supercells. This figure has drill holes displaying the sodium-calcium depletion index developed by MDRU as part of their porphyry vectoring project. The goal of the index is to indicate areas of highest and lowest advanced argillic alteration, which is typically associated with the epithermal environment above copper porphyry deposits. So you can see more advanced argillic alteration is indicated by the reds and magentas, and they are all concentrated in the northeast in the area of the supercells. Advanced argillic alteration is characterized by removal of calcium and alkalis. So potassium levels are preserved by the influx of potassic alteration. So this depletion index compares sodium and calcium to immobile elements such as the rare earth elements or aluminum. A higher index score corresponds to higher advanced argillic alteration and suggests a cooler depositional fluid temperature in an environment above the porphyry. In our case, assay data shows advanced argillic alteration increases to the northeast across the deposit. Interestingly, this northern margin of CS600 transitions to gold dominant rather than copper dominant and appears as a gray sericite altered intrusive breccia rather than a pink coherent intrusive that I showed earlier. These observations have led to a theory that possible overprinting epithermal mineralization and alteration is being supplied by a structural conduit in the northeast. Again, this is what we know about structure so far. There are 4 stacks of parallel planes of quartz carbonate, sulfide veining, and breccias traced across 400 to 800 meters. They're focused at the northern part of the deposit, and they are oriented obliquely to the main mineral domains. So plotting that information on a stereo net, and this one displaying poles to planes, some observations that can be made interpreting this relationship are the main resource domains in blue, in that blue circle, are roughly parallel to Treaty Thrust Fault 1, or TTF1, as the dominant structure in the deposit. The Route 66 domain is parallel to Supercell 1 domain, and Route 66 also lays outside the main deposit boundaries and may represent another supercell on the southern side of the deposit. Supercell 1 is oriented approximately 35 degrees obliquely to the dominant deposit orientation, and this may represent a conjugate fault set exploited by SC1 mineralizing fluids or an evolution of the stress regime by the time of SC1 deposition. So looking to geophysics for more clues, an interesting anomaly presents itself as a coincident magnetic low anomaly and a planar resistivity low anomaly. And that's interpreted to be a fault that overlaps with the location of SC1. The image on the left is a plan view from our 2022 Airborne Magnetic Survey, where blue represents low magnetics and pink represents high magnetics. The image on the right is a cross-section from our 2016 Ground MT survey, displaying low resistivity as purple and pink and high resistivity as light blue and white. SC1 is marked by the red circle, and the interpreted fault is marked by the dashed white line in both plan view and cross-section. Considering the fault's proximity to SC1 and the interpreted shift to advanced argillic alteration in this area of the deposit, this may represent our theorized northern structural conduit for epithermal mineralization. And if it is potentially a hydrothermal feeder structure, then there exists the potential to find more supercells, and more importantly, the potential to find bonanza-grade ore shoots. Using the observations and clues we have gathered so far, we are continuously working on our SC1 theories and part of that is fitting into the big picture genetic models like Dick Silito's on the left and Greg Corbett's on the right. The CS600 easily fits into the central porphyry copper-gold causative intrusion, but SC1 displays characteristics of a few families of transitional porphyry epithermal mineralization, including intermediate and high sulfidation epithermal veining. It's common for gold-rich copper porphyry systems to be overprinted by higher gold grade epithermal veins, and there are a variety of mechanisms responsible for this. Two dominant mechanisms for the superposition of epithermal systems on porphyry centers have been identified. In the left figure, the first image at T0 shows a typical porphyry copper system elongated from a deep-seated magmatic source through the porphyry intrusive dikes and potassic altered core zone and reaching up through phyllic alteration to a lithocap kilometers above at the paleo surface. T1 shows the first mechanism for superposition involving rapid uplift and unroofing over a very short time span, such as 10,000 years. This causes the same magmatic hydrothermal system to telescope downwards by decreasing the vertical distance to surface and triggering meteoric water mixing, boiling, and precipitation of epithermal mineralization in reactivated structures cross-cutting the initial porphyry body. T2, on the other hand, shows minimal uplift and erosion, but rather displays superposition of a much younger magmatic suite with its own associated porphyry and epithermal mineralization on an older porphyry system. Either way, we have a lot more to look for. Researching controls on epithermal mineralization in the deep porphyry environment, I came across this figure on the right by Li Wang et al. From their 2019 review on intermediate sulfidation epithermal deposits, and found it to look eerily similar to the relationship of our SC1 and CS600 domains. They were depicting an integrated model for the structural control on metal transport and deposition in intermediate sulfidation and likely other epithermal systems. They noted that many mineralized veins were found tightly associated with pre-ore dikes and interpreted that the dike contacts created a physically discontinuous plane that could be reactivated as faults that could provide conduits for mineralizing fluids. This applies directly to SC1 in two ways. The upper contact of the CS600 is nearly always recognized by a meter-scale mineralized quartz breccia with excellent gold values, which may suggest that CS600 itself provided the structural conduit for the SC1 mineralization. Additionally, the lower supercells, SC1C and SC1D, are often texturally associated with a microporphyritic rock that may actually be a pre-ore dike providing a conduit for SC1 gold fluids. So to determine what type of scenario we could be dealing with at the Goldstorm deposit would require more academic studies to review the fingerprints of our various styles of mineralization. We're currently working on petrography, geochemical, and structural analysis to further our understanding of SC1, and ideally we would engage in more geochronology as well as fluid inclusion studies to test our working hypotheses. Ultimately, we're still very early on in our discovery process, and we're hungry to find more high grade, so we're going to keep drilling. Thanks very much. And if you like these videos, please consider liking and subscribing. Cheers.